Okay. Posso começar, então? Bom dia a todos. Meu nome é Geraldo e sou coordenador do EOLAB, do Earth Observation Laboratory, que é um laboratório vinculado ao Instituto de Ciências do Mar da Universidade Federal do Ceará. Eu gostaria, em nome da organização do evento, dar-lhes as boas-vindas ao workshop de Hidrologia Espacial 2021, Novas Perspectivas e Missão SWOT. É importante ressaltar que este nosso encontro está sendo possível graças à parceria do EOLAB com o ERD, na pessoa da doutora Marielle Gossetti, e o apoio do Consulado da França. Também nos ajudaram na organização a FUNSEM e a Orbit, Satellite Water Monitoring. Meus agradecimentos a todos esses atores que tornaram possível esse momento aqui que nós estamos vivendo. Nesses 2 dias de workshop estaremos nesse grande auditório virtual, recebendo 12 especialistas da área de satélites para tratar de uma temática muito importante, principalmente para regiões semiáridas, onde o recurso água é um bem extremamente precioso, e regiões costeiras, onde milhões de pessoas vivem. O tema do workshop é a hidrologia espacial e a missão SWOT, Surface Water Ocean Topography. Pois sabemos que, quando o oceano canta, o clima dança. E as condições dinâmicas e termodinâmicas dos oceanos, principalmente o Atlântico, impactam no clima da região semiárida do Brasil. Observar a Terra a partir do espaço, em sinergia com a futura missão SWOT, um satélite dedicado ao estudo da topografia dos oceanos e da dinâmica dos corpos d'água, dos corpos d'água superficiais terrestres, irá abrir novas perspectivas para as áreas da oceanografia, hidrologia, previsão climática, entre outras. Antes de passar a palavra para a doutora Marielle Gossetti, um aviso. Durante a palestra, as perguntas podem ser colocadas no chat. Após cada palestra, dentro do tempo previsto, elas serão respondidas. As que não forem respondidas dentro do tempo previsto para a palestra, nós enviaremos um e-mail com comentários. Bem-vindos novamente, e passo agora a palavra para a doutora Marielle Gossetti.
Bonjour à tous, hello, welcome. Je pense que je vais parler en français puisqu'il n'y a que des lusophones ou francophones actuellement connectés. Donc, merci à tous d'avoir répondu présent. Nous avons pratiquement 160 inscrits à ce workshop virtuel, malgré une confirmation tardive de l'événement. Donc, merci à tous, en particulier merci aux 12 personnes qui ont accepté de faire des présentations. Évidemment, comme l'a dit Gérald, nous aurions préféré faire ce workshop en présentiel qu'en virtuel. Il aurait dû se tenir il y a quelques mois au sein d'un événement qui s'appelle Space Week Nord-Est, qui n'a pas pu se tenir cette année pour les raisons que nous connaissons tous de pandémie. Mais nous espérons faire cet événement en présentiel en 2022 et vous y serez tous conviés. Le nombre d'inscrits, évidemment, montre bien l'intérêt très universel des thématiques qui seront abordées, eau, cycle de l'eau, ressources en eau, et surtout l'intérêt du spatial pour mener à bien des études sur ces sujets. Il y a un grand intérêt, évidemment, pour la mission SWOT, qui va arriver d'ici un an. Ça va être une véritable révolution dans le domaine de l'hydrologie. Et nous sommes contents d'avoir cette opportunité de présenter une nouvelle fois SWOT et où est-ce que le satellite en est. Et puis, de profiter d'avoir ce panel d'experts qui vont revisiter la question de l'eau, comment on peut l'observer par satellite, quel que soit son endroit, dans l'atmosphère ou dans le sol. Et une ressource particulièrement cruciale dans le Nord-Est et semi-aride. Voilà, merci. Nous allons maintenant laisser la parole à notre premier présentateur, Nicolas.
Bonjour à tous. Marielle, currently I cannot share my screen. I will wait for this authorization. So welcome all. And I'm very pleased to be today, I will say, part of this WebEx meeting. As said by Marielle, it would have been much more convenient. Oops, I'm now able to share. To be in a face-to-face joint meeting. But that is life, and we have to accommodate for this kind of problems. So first, do you all hear me well?
Yes, very good.
Okay, so I can go on. Marielle, I have also one question. How do you manage the translation, and how do we manage the question raising from the room? Shall I make some breaks at some point?
So people will ask questions through the chat.
Okay.
And after your talk, we'll ask you the question.
Okay.
The translation is now going on automatically, and people can choose. They have a button with interpretation, and they can choose to hear the talk in English, or the original, which is now in English, or in Portuguese.
Okay, perfect. Thank you. Thank you, Marielle, for this clarification. So I will present some materials regarding how the space satellites can contribute to the monitoring of the hydrological cycles over the Earth. I will not go into all details regarding the different missions that I will present in a few minutes from now, and I will make a focus on the SWOT missions. The SWOT mission is to be launched in 1 year from now, roughly, and I am very pleased with my colleagues from the different institutes to work on this very, I would say, promising new techniques that I will describe later on. So as said by Marielle, do not hesitate to raise questions on the chat. If we have time, we will reply to the questions during the meeting. If not, I promise to send a reply by means of emails or any means that would be convenient to the board. So just a few words regarding the hydrology and the space contributions. As you may know, which is very well known by many of us, observing water from space is a very, I would say, important means to complement what we can observe with the in-situ means. On the left-hand side, top panels, you can see the GRDC worldwide database, which provides the in-situ data regarding the reverse discharge. As you may see, we have some area which are dark blue, which means that we have nearly routine data provided on these countries. But in many countries, you see that we have a very sparse data coverage, and even the data available are very old, sometimes dated in the early 19th centuries, which means that we do not have a full visibility, understanding, monitoring provided by the in-situ networks today regarding the hydrological cycle evolutions, either as a consequence of humankind or climatological evolutions. An important point also is that we make use of both in situ and space. We do not oppose one to the other. Both are very useful and complementary. So the space techniques can complement in situ, and in situ will complement space, but both are of interest and are required in the near future. For example, if we forget a bit the inland waters surfaces and we talk about ocean surfaces, we have a dense network of tide gauges and buoys, the Argo networks, that efficiently complement what we can observe with the space satellites available in routine. And all those data are assimilated in models today. This is what we need to do for the hydrological cycle observation in the near future. So for the in-situ data, in a few words, the networks are not regularly spread, as you can see on the map. We have less and less stations in services, in particular in some countries, for example, in Africa. But even in Europe, as you can see, for example, for Spain, we do not have access to the data acquired over this country. It means that maybe we have some data available at the country level or a local level, but we do not have access to those data in an open framework. The access to the station can be difficult, dense forest, mountains, and we often discuss that point with Stéphane Calment regarding what we can do, where we can install some station, and to compare the in-situ validation information towards the satellite ones. The access time to data may be very long. Sometimes it takes weeks to go to visit a site. And data, as I've said, are not always shared at international level. And this is where satellite data play a very large role, because space techniques are now global, repetitive, homogeneous, and fully operational. Since a couple of, I would say, years from now, thanks to mostly Copernicus constellation services, we have access to a global monitoring and survey of the whole Earth, and we have now to play and to process the data to analyze how it evolves from time to time. A simple schema as well. We have here the different parameters where some satellite data can contribute in terms of monitoring and observations. So as you can see, we can observe nearly all of the water cycle's different compartments. Even the soil, moistures, the groundwater, the river's discharge, the lake surfaces, the snow, the ice, and so on. So we have a very good observation capability provided by the satellite. It has obviously some limitations in terms of spatial resolution, in terms of temporal resolutions. We are not always, I would say, we do not have always, I would say, enough data to play with. For example, if you'd like to observe a tiny rivers, which can be very rapid, the space satellite data will provide you observation roughly every week, not faster. So it means that in those cases, you need to complement it today by some in-situ data. In the near future, maybe some new satellites will provide an additional, I would say, temporal coverage. Another way to illustrate these water cycles, precipitations, we can use some optics, infrared, radars, and we have several missions to play with. Regarding the surface states, surface waters, evapotranspirations, discharge, water body surfaces, water level, water quantity, water temperatures, water extent, even in some cases, bathymetries. All those parameters can be derived from one satellite data or the others. It is the same for soil moistures and even for groundwater. Last but not least, another schema to illustrate the different contributions. So as you can see, and this is only what I like to illustrate here, is we have today a very large panels of different satellites to play with and to look at, to
Recording
better
stopped.
understand the satellite, the hydrological cycles
Recording in
worldwide.
progress.
The recording was stopped for a few minutes. Do you hear me well yet?
Pas de souci, on t'entend très bien, Nicolas.
Merci, Marielle. So that's all I want to say regarding the short introductions. I just also want to precise that all those slides are publicly available on the web portal. So if you'd like to use it, if you'd like to use some of it, feel free to do so. We have just, I would say, a copyright, but it is open materials for you in the near future. So now I'd like to present the SWOT missions in more details on what we are currently developing, on how we are excited before the SWOT launch in a couple of months from now. So first, some words regarding the objectives and applications that are around the SWOT mission. So SWOT means surface water and ocean topography. It's a brand new satellite concept for the study and monitoring of both inland waters and the oceans. It is the first time that we have a satellite devoted to the inland waters volume determination worldwide. In the past, we have used nadir satellite data, and maybe Stefan will come back on those satellites. But for the first time with SWOT, we will have a complete coverage of the Earth and the complete coverage and monitoring of the inland water cycle. This mission is a partnership between NASA and CNES with some contribution from the Canadian Space Agency and the UK Space Agency. Currently, the satellite is in France, in France, to perform what we call the integration and test of the satellite and the payload. Everything goes well. We have a very large team in Cannes, very close to, I would say, Italian boundary, where both NASA JPL and CNES and the industry around that satellite body are working hard to make sure that in a few months from now, we will have some actual data to play with. This cooperation is based on 25 years of cooperation between CNES and NASA, maybe even 35 now. We started in the late 80s with TOPEX Poseidon on the JSON satellite family indeed. The main information provided by SWOT is not regarding water quality, but it is regarding water quantity. So SWOT will measure and provide the information regarding the water levels of rivers, lakes, flooded areas, and it will improve the ocean observations. Last but not least, SWOT will observe the estuaries on the coast. It's a continuous information from the inland waters to the ocean and the rivers. So we'll have a very good information to link both surfaces from the land to the ocean and rivers. As you may know, the management of the water is very difficult worldwide. It is also clearly pinpointed with the geodesic graph that I have used for the first slide. The sharing of river waters often cause frictions between neighboring states. And when we mean frictions, it can be wars. SWOT will provide for the first time a global information as input for system monitoring river basin and for verifications. And with some colleagues, Marielle, Stefan, and many others, we wish to have the capability to do forecasts. So to implement progressively assimilation techniques, to use the observation to predict our features. This is a very demanding activity, but we have many ongoing activities in Brazil, in France, and in other countries to progressively put this system in place. One figure to keep in mind, nearly 40% of the world population lives in river basins shared by at least two countries, It means that they are very sensitive to potential friction or crisis between the two countries. And this is increasing from year to year. Many people are coming close to rivers to have fresh water available, and the crisis it will certainly rise in the near future. SWOT will also provide more accurate weather and climate forecasts. This is particularly true for the oceans. It will enable a more accurate weather and climate forecasting, especially seasonal, by providing better initial and limit conditions for ocean surfaces and hydrological conditions. Over the oceans, we have today quite good observation techniques, but we know that we are a bit blind. We miss a lot of information. Roughly 50% of the ocean circulations remains today unknown to us, just because we do not have the sampling, both in space and in time, to observe the ocean's dynamics worldwide. We use the satellite data available today. We have very accurate models, but we need to make a step further to better understand how the ocean will react as a consequence of the global warming. One figure to keep in mind as well, nearly 30% of the world gross domestic product, the equivalent of $18 trillion in goods and services, are weather dependent. It means that we are very sensitive, obviously, to Earth's surfaces or to the Earth's state. So we need to improve our capability. We need to sorry, but I get some messages in the mic. So we need to improve our capability to better predict what will be our future in terms of Earth environment, hydro availability, weather forecast worldwide, to account for the ongoing climate change evolutions. SWOT will also provide us some new features to help us better managing fresh water for urban, industrial, and agricultural use. As said, for the very first time, it will provide the first inventory of the water worldwide. Whatever the boundaries of the country is, we will observe North America, we'll observe South America, we'll observe Africa. It will be a global and full picture of the inland waters characteristics worldwide, open data available to all. Another figure to keep in mind, the world's water service generates turnover of roughly 125 billion per year. It means that we have a very large market. Today, the market is not using so much satellite data, but with our colleagues mentioned previously, we are working in that direction as well. SWOT will also help us improving our knowledge and enhance observations. All these areas and more stand to benefit water resources, natural risk, biodiversity, health, agricultural sectors, energy, territorial development. This is valid for inland waters, for the land surfaces. This is also valid for the coast surfaces and for the ocean surfaces. Now I'd like to describe briefly the spacecraft and the instrument. This is a picture of the SWOT satellite. Just to keep in mind that this is a pretty wide and large satellite body. The weight is of the order of 1,200 kilograms. The size is of the order of 20 meters for the solar panels. And what you can see here, what is called the careen, is a mass with a length of 10 meters. So this is a pretty Why satellite? Pretty costly indeed as well. The cost of this satellite is roughly $1.2 billion. And the main instrument is what we call the carrying instrument. We have some other instruments on board the satellite that I will briefly describe. We have a standard GPS to perform the actual precise orbit determination, which is complemented by the Doris system, developed by French 40 years ago, roughly. We have a laser reflector to calibrate the accuracy of the orbit in routine. And we have a standard nadir payload with the altimeter and the radiometer, very close to the ones that are embarked on the currently flying mission like Sentinel-3 or Jason-3. This is what Carine will provide in terms of, I would say, data. For both the oceans and the inland waters, for the first time, we'll have to play with an image. Currently, what we call the satellite altimetry missions provide the information only where they fly, only at the nadir point. It means that on the right-hand side and on the left-hand side, we are fully blind. The nadir satellites, which we are using today, have a strong limitation in terms of spatial coverage. SWOT will provide for the first time this image, which is similar to what we can observe with the SAR concept, but the SAR does not provide at all the topography. Thanks to the interferometry, and we will describe very briefly the concept of the interferometry baseline, we will have access to the actual surface water topography over land and ocean topography over the oceans with an accuracy with a very good accuracy. The source is of the order of 50 kilometers on both sides. 50 kilometers on the right, 50 kilometers on the left. It's a two-dimensional image. It's using interferometry to estimate the height of the waters, of the inland waters, the height of the oceans, and maybe the height of some ice caps, if the surface is flat enough. It is based on the quite classical synthetic aperture radar processing. We are using a K-band emission sources, and we make use of two synthetic aperture radar antenna at the opposite ends of a 10 meters boom. This is what we call the baseline, and which is the basis of the interferometry concept. So you have two antennas on both sides of the satellites. And at the end of the presentation, I have three different videos which will illustrate the concept again. Regarding the nadir altimeter payload, this is a very classical one, what we call Poseidon 3C, which is very close to the one which is currently flying on Jason 3, which was close to Jason 2 and close to Jason 1. Jason 1 was launched in progress. 2001, 20 years ago, and we have not made much evolution on this altimeter design since then. We have just improved its capability to monitor inland water surfaces thanks to what we call the open loop tracking modes. The nadir altimeter is an independent instrument, so it will be used as an independent source of information, but it will complement and calibrate Carine, and it will also fill the gap at the middle of the gap, at the middle of the swaths that are highlighted here, as you can see. We have a radiometer, which is based also on the readage coming from Jason 3 missions currently flying, using three separate frequency channels, a longer readage, roughly 30 years of development by JPL, we have indeed two different antennas for the radiometer. One will observe the wet tropospheric correction on the middle of the right-hand side, and the other on the middle of the left-hand side. The radiometer is used to determine the path delay of the altimeter signals due to the atmospheric water vapor and liquid water in the atmosphere. It is used only over oceans. The radiometer today is not to be used over land surfaces. Over land surfaces, we make use of empirical models provided by ECMWF or others. The RIS system, as said in introductions, the RIS is a system used to determine in real time and offline the actual position of the satellite over its orbit. It complements the GPS system in terms of observation and accuracy. With the RIS and with GPS, we have the capability to determine the satellite position within 1 centimeter on the radial component in offline. In real time, we can determine the position of the satellite with an accuracy of the order of 3 centimeters only in the radial component again. This is very important because it can be used to generate some, I would say, real-time observation on real-time products that can be ingested in some operational models to better monitor the evolutions of the oceans or of the inland water states. The RIS is based on a network of 50 ground stations transmitting signals at 2 frequencies to the satellites. The receiver on board the satellites analyzes the received signal frequency to calculate its velocity. It's a Doppler shift frequency. And this velocity is then fed into orbit determination models to derive the satellite position on orbit. The GPSP, you know, everybody knows GPS. So we have a very accurate GPS on board the satellite. It is used to track signals. The GPS on board SWOT do not have the capability to track Galileo signals.
Recording stopped.
Its performance requirements are based on heritage Gen 3 capabilities. It has quite similar performances than the DORIS-1 in terms of accuracy and precision. The instrument
Recording in progress.
Development is part of a common block buy for SWOT and Sentinel-6. Sentinel-6 GPS provided by JPL being in operation since roughly 1 year. To complement those two POD instrument techniques, we have what we call the LRA, Laser Retroreflector Array, which is only some mirrors which are used with some laser station on ground to send a pulse and to monitor directly the distance between the laser stations and the satellites. This is very used to calibrate and to compare the accuracy of the different models that we implement to determine the satellite positions in routine. Regarding the orbit, for this SWOT mission, we have 2 different orbits. On the right-hand side, top panels, you see what we call the scientific orbits. The scientific orbit is a 21 days orbit cycle in terms of repetitions. It means that for one particular path, you will observe the same location only every 21 days. 21 days is a bit, I would say, long time, but this was a compromise to make sure that we observe the whole Earth. We have another orbit, which is called the Calval orbit. And as you can see on this plot, and I have another one later on, this Calval orbit observe part of Brazil, observe part of the France as well. During this Calval orbit, we will observe for a short period, only 90 days, every day, the same orbit, the same rivers, the same lakes, and we will for sure observe and understand a lot of very high frequency phenomena thanks to these 90 days durations, 1 day orbit that will be provided by the satellite. This is another view of what we call the fast sampling of Brazil on Maroni rivers and others. Again, it will be very, very interesting to look at those data. Every day, we'll observe the same situations, but not exactly at the same time. We are not sun synchronous. So from one time to time, we'll have a different time of observations. It will change from one day to the other, roughly of the order of 10 minutes. So thanks to those data, which is very unique in terms of observation capability, we will see and observe and better understand rapidly changing phenomena over those particular orbit phases. And with Marielle, with Stefan, and with all our colleagues, we pay a lot of interest over this orbit for both the Calval, calibration and validation, but also for the science, what we will observe during this 1 day observation phase, which will not be as feasible during the science phase. This view graph illustrates the different coverage over France. I do not have the same over Brazil, and I do apologize for that, but we can maybe make this the same kind of, I would say, animation later on. Just on the right-hand side, you have the number of days, which change from time to time during the orbit cycle of 21 days. This animation is just there to highlight and to illustrate what we will observe and by when on a quite small country like the France one. And as you can see, sometimes, some days, you do not observe at all France. And sometimes, some days, we observe it twice. And this is then gathered into this kind of view graph, where we gather the different orbit numbers which will observe SWOT France, rivers, and lakes during the 21-day cycles. Maybe you can see it on this graph. It will be clearer on the next one. We have some overlaps. Some part of the world are observed several times, and sometimes we are fully blind. And again, we illustrate that graph over France, and again, we can maybe generate the same one later on over Brazil as a matter of illustrations. For some rivers and some lakes, we have no observation at all. SWOT is global, but somewhere, I don't know if you can see it, we have what we call some diamonds where we are blind. This is related to the swaths of 10 kilometers up to 60 kilometers. So from the nadir to 10 kilometers, we do not have some observation at all, which generates those teeny gaps. So we have some teeny gaps, but in some cases, even during the 21-day cycles, we will observe the rivers up to 4 times at a latitude of the order of 40 degrees. This is latitude dependent. So for all latitude roughly around 40 degrees, we will have this kind of, I would say, observation capability provided tomorrow by SWOT missions. So it ranges from null up to 4 times. And when we speak about, and when we talk about calibration, validation, obviously we'd like to have in situ means installed where we have more observation acquired by the satellites. In other words, we will certainly make more efforts in this kind of area than when we will have only one unique observation provided by SWOT in terms of in situ calibration deployment. Regarding the launch is today targeted for November the 22nd, 2022 on a SpaceX Falcon 9 rocket from Space Launch Complex at Vandenberg Air Force Base in California. Today the schedule is okay, so we are still hopefully waiting for a launch of SWOT mission in 1 year from now. A few words regarding the ground segment, just for information. I will not go into details regarding this. It's quite complex. We have a lot of acquisition stations because the telemetry is quite large. We are downlinking roughly 7 terabytes per day in terms of telemetry that needs to be sent from the satellite to the ground station and then to the processing centers. On this chart, just keep in mind that we are working in close cooperation between CNES and JPL. But not only CNES and JPL, we are working in close cooperation with the scientific team, which is involved largely into what we call the science data processing centers, where we will implement the algorithm and where we will implement the actual product to be delivered later on to the end users. So we rely on a large team at project level, but largely supported by our PIs from the science team. A few words regarding how SWOT will work regarding the interferometry. Interferometry is indeed quite, I would say, simple. One of the antenna, which is named A2 in this view graph, is the antenna which will send the pulse. We have always the same antenna that will emit and send the pulse towards the surface. And we use two different polarization, H and V, to make sure that what we observe on the left-hand side will not be, I would say, degraded, but the signals coming from the right-hand side. There is the A2 antenna will send the pulse on the left-hand side, and thanks to the roughness of the terrain, we will have some scatters, and the electromagnetic wave will come back to the satellites on both A1 and A2 satellites. The same is valid for the V polarization. This is just a small video that illustrates how it will play and what we can analyze later on. Again, continuity. We observe the oceans, then the land then the oceans. We have a very good and continuous monitoring of the oceans, the coast, the estuaries, and the inland waters and the rivers. This will be very, very, I would say, new to the science team, and for sure we will play a long time with the SWOT satellite data in the future. So I said, to summarize, one of the antenna emits towards the left and the right hand side, each with a different polarization of the radar wave emitted, and both antenna are receiving the signals. If you compare the SWOT incidence angle with the other satellite techniques, we are using very different angles. The standard SAR, like Sentinel-1, TerraSAR-X, or the scatterometers, use an incidence angle of the order of 20 to 60 degrees roughly. SWOT will observe over these very small angles between 1 and 4 degrees, very close to the nadir view indeed. And this is why with this very small, I would say, incidence angle, we have a quite limited interferometry map, limited to 120 kilometers only compared to the other satellites like the scatterometers and the SAR-imagers. Why have we selected these incidence angles? Just because we need to make sure that we will receive some power back from the surface. So first, we are not using nadir because we are otherwise we cannot have some interferometry measurements, but we cannot use incidence angle as high as the SAR wants, because for SAR imagers, often, the inland waters often are fully dark. There is not enough roughness, so there is not enough power return over inland waters. This is why we make this compromise between 1 and 4 degrees incidence angles. Also, we have to make the compromise between the inland waters requirements and the oceans requirements. SWOT is a dual mission, observing both surfaces. And when you want to observe both the ocean and the inland waters, you have to make a choice, which is a compromise between the constraint coming from one community and the others. We make use of the Ka band, which is an heritage from the currently flying SARAL missions, which is also used by the GPM missions, just because we have a less specular reflections, we have a smaller spacecraft antenna base, a smaller footprint, and a better signal-to-noise ratio. In terms of geometry, interferometry is, I would say, pretty simple. It's just a triangle approach techniques. You measure two different distance. You can make the differences. Knowing the angles, you can derive the information regarding the height of the surfaces. The height of the satellite is derived from the DORIS and GPS, as we said. And by using directly the interferometry informations, you measure the height over the inland waters, rivers and lakes, wetlands, and over the oceans. I don't go into details regarding those simple equations, but you have it available in the presentation later on if required. Already said, why use interferometry? For the very first time, we will have images of the topography. For sure, it will be a revolution for our inland waters community. We today are quite blind in terms of snapshots and observations due to the nadir observation provided by the currently flying satellites. With the SWOT imagery, we'll observe very short, small-scale signals over rivers and over lakes, which are today fully not known by the community. I will skip that one, and I will describe a bit what we call the pixel geometry on the SWOT. As we say, the both antenna at the end of the mass receives the radar wave reflected from both ways, from both sources. And the succession of the pixel across the SWOT are derived from the time it takes to the wave to return to the satellite. As you may see over there, related to the interferometry and to the distance between the point at the surface and the satellites, the size of the pixel is not continuous. It ranges from roughly 60 meters up to 10 meters. It is larger close to the nadir. It is smaller at 60 kilometers away from the nadir. So this is something that we have to keep in mind where we will analyze the data, because the surface will be an average of what we have observed over a cell, which is of the order of roughly 2 meters multiplied by 60 meters on these directions, close to the nadir and multiplied only by 10 meters at 60 kilometers away from the nadir positions. This is also illustrated here again, just to keep in mind that the size of the pixel is a function of the distance to the nadir. So to make sure that we account for those kind of evolution related to the interferometry SAR imageries, we need to account for it in the ground processing. Among the processing, we have some averaging that are done on board, and we will further average on ground the information to reduce the noise. In terms of onboard averaging, we have what we call the low rate mode, which is only used over open oceans. It's available worldwide. It's a continuous mode, which provides low rate informations. When we mean low rate, it means pixel of the order of 250 meters square. I have not described here those modes because this is really mostly devoted to open oceans, but it can certainly be used for large rivers or large lakes over some inland waters situations. On the on-ground, for what we call the high rate mode is over land and coastal waters. We will process those pixels to average those and to make sure that we provide information which is dependent on the inland water bodies characteristics. In terms of dark waters, this is exactly what we will face. If you have a low rigorosity, you have a strong geometry. It means that at the nadir point, and Stefan knows it very well, when you send the pulse, everything, all the energy will come back to the satellites at the nadir point. But as soon as you departure from the nadir point with a very low rigorosity, you have this kind of phenomena. Very few or not at all energy will come back to the satellite. If you have a stronger rigorosity, you are less sensitive to the incidence angle used. What will be the value added for information provided by SWOT? So as we said in introduction, SWOT for the first time will measure the height, the width, and the slope. We do not have the means to directly compute discharge or volumes, neither the current speed. The product will provide discharge, and the product will provide lake storage evolutions, but it will be computed remotely offline through different high-level techniques. Over the rivers, the hydrologic equations Manning are used to compute the discharge by error minimization of the equations. It's a very complex approach, and we have a very large team working in this development, and this is a very demanding and I would say ambitious works to compute worldwide the river's discharge without any a priori knowledge over the bathymetry and other Manning equation parameters. Some more regarding the SWOT hydro products, and I propose to make use of two videos. This kind is only a screenshot of the Aviso web portal, which describes the river products, and that one, the lake surveyor product. I'm just on time, so I propose that I just send a video that will be much better explain that how the SWOT product will be generated over rivers. Marielle, do you see my screen? Still?
Yes, we see the presentation. We don't see the video.
Okay, you don't see the video. This is what I want to make sure. Means I'm just the difficulties to Hop, nouveau partage. Marielle, do you see now the video?
Now we see the video. It's not playing yet, but okay, now it's playing. We don't have the sound. But... We see the video, but we don't have the sound.
I understood, Marielle, but I don't know how can I make sure that you have the sound. So
okay, never mind. It's okay.
Yes, the video will be available to the audience. So maybe we just go through it and. So SWOT will provide height, width on the discharge. Here we illustrate the nodes on the cycle average provided by SWOT. You see that we observe the scene several times. Over these 21-day cycles, you observe it 3 times, 2 times, or only 1 time. And we will make the average of this kind of information over a cycle basis. So this is it for the rivers, and I do apologize for the fact that you didn't get the sound. The same for the lakes. So SWOT will provide information over big and small lakes. The first information is regarding the water surface, the area, and the height, and the change in water volume. If you have the a priori bathymetry information available, you can compute and determine the volume evolutions. We will do it for a single pass, but we will do the same for other cycles. In terms of observations, like for the rivers, we will make a mean observations on the 21 cycles. And in some cases, the lakes is observed by 2 different bases, and we'll make sure to efficiently combine those different informations. This is also valid for these very large lakes, for example. And the last video is regarding the SWOT mission, 2-minute illustration, no sound at all. The text is written on the screen. That's it on my side regarding the SWOT, I would say, presentation. Honestly, every time when I look at those videos, I'm so excited. I'm so excited to wait for those data, and I'm so pleased to be part of the game. I'm so pleased. So, gentlemen and women, thanks for your for being part of this. I would say new story. It will be a revolution for sure in 1 year from now, and I hope that you will be part of the game. I give you the floor, or Marielle.
Okay. Thank you very much. Thank you very much, Nicolas, for this great talk, very pedagogic. I think you made a lot of new future SWOT users and students and researchers in
we hope so.
the last hour.
We hope so. You know, Marielle, that we need many people to analyze the data.
Yes. So I think you created vocations there. Excellent. Thank you.
Thanks to you, Marielle.
I'm very objective about it. we have a question.
Yes, in Portuguese.
Yes. So I'm going to translate it as much as I can. It's about the rugosity, the fact that the behavior of the signal is different depending on the type of rugosity of the surface. And so Pablo Santos is wondering if that means there will be some problems with the precision of the data, especially in rivers which have a high quantity of sediments.
A high what?
Quantity of sediments, a large load of sediments.
I don't know if the sediments can play a role. Indeed, this is actually one of our fear, what we call the dark waters. And we have done some experiment with the Earth water on board a spacecraft, which demonstrates that yes, indeed, in some cases, the water is too flat, too mirror. We do not have enough energy sent back to the satellite. In other words, we do not observe it. It will happen for sure, because we all know that in some cases, the surface can be like a mirror. And in those cases, we will have certainly a strong limitation for SWOT in terms of observations. But obviously, and hopefully, it will not occur every time, everywhere, every day. From one day to the other, from one time to the other, the rugosity change, mostly as a matter of wind frictions, but also current speeds. So I would say yes, this is something that we all have in mind in terms of limitation, in terms of observations, but for sure, even if we lose or we are blind regarding 20% of the data, it will be season dependent. It will be time dependent, and we will learn so much with the SWOT data worldwide that this limitation will be will be forgotten very fast.
Okay, thank you very much. I don't see any other questions. I have one. I would like to know, can you elaborate a bit about how SWOT might be disturbed by in places where there is a lot of relief, like cliffs next to the river, and high-level vegetation?
Good question as well, Marielle. SWOT is a pathfinder. So there is plenty of things that we are going to learn with the satellite data themselves. We have tried to anticipate, and we have developed with JPL the SWOT satellite, and we have also developed other means to try to better characterize what kind of signals we will observe with those incidence angles at the Ka band frequency. But we will have some surprise, some good ones and some bad ones. It will depend on the roughness, on the characteristics of the terrain. For example, if it's some rocks emits very low energy back to the satellite. So in other words, you will observe only the surfaces which sends back some energy to the satellites. It will not be the case, for example, if you are observing wet sand or wet mud, which can be very bright for SWOT satellites. So yes, we have also those kind of, I would say, limitation or observation on point to be taken into account in mind. On the data processing algorithm that we are developing, we'll try to make sure that we use only inland waters pixels and to discard the pollutions that are coming from the cliffs or from other phenomena. Regarding the high vegetations, I don't have so much fear because we observe very well the inland waters with another instruments at the K-band, and this is done with the SARAL missions. On the radar electromagnetic waves is mostly, I don't know the name in English, so je vais le dire en français, tu vas traduire. C'est sensible plutôt au tronc et pas aux feuilles des arbres.
Thank you very much for this difficult translation. So I would say the trunk of the tree. It's more sensitive to the trunk, so to the wood of the tree, than to the leaves, which are a bit lighter.
Canopy.
Ah, ok, canopy. Stéphane, est-ce que tu peux traduire l'autre question, s'il te plaît? Em relação aos levantamentos como SWOT, qual a pegada footprint?
En français? Traduire en français pour Nicolas?
Comme tu veux.
Plutôt en anglais, que tout le monde comprenne, en fait.
So there is a last question. About the measurements by SWOT, what is the footprint? What is the size of the footprint of the individual measurements?
Over there, this is the size of the pixel indeed.
Specifically for SWOT.
Yeah, for SWOT, we don't think about footprint. We make use of the SAR processing technique. On the footprint is the pixel size, which I have tried to explain on the slide number. I don't know even this one. So we cannot compare SWOT with the classical nadir altimeters, which make use of footprint of the order maybe up to 10 kilometers radius. Over there, thanks to the SAR altimeter, to the synthetic aperture processing performance board, the footprint size is this pixel size. It's of the order of 10 to 3 meters only on this side of the source, 60 meters to 2.5 meters on this side of the source. So it's a very, very small, but it's very noisy. So those pixels will be, I would say, average on ground to make the different rivers and lakes products that we have described in the video.
Okay, thank you very much, Nicolas, and a big applause again for this excellent
Merci encore, Marielle.
It was really great. And now we are going to dream more by seeing what can be done on the ground to compare in situ data in nice rivers with satellite information. So, Stéphane Calmont, you are welcome.
Okay, so I'll try to share my screen. Comment on fait ça? Pas de bouton pour partager mon écran. Ah si, écran partagé. Ok. Ça y est. Vous voyez mon écran, la présentation?
À part que tu n'es pas encore en mode présentateur. Si, parfait, parfait.
C'est bon? Bom, bom dia a todos. Então, bom, posso falar em português, mas vai ser pesadelo para vocês, então vou falar inglês. Acho que a voz do tradutor será bem melhor que o meu português. So, I am Stéphane Calment. I am a researcher from IRD, and right now I am in French Guiana, so I am your neighbor. We share a frontier, and which is a river frontier, so it's very interesting in this context of the SWOT mission. So what I was asked to present here is field work that we conduct for the validation of the SWOT satellite. And as it was very brilliantly showed by Nicholas just previously, SWOT will be a game changer for monitoring the rivers. But because of that, we have many questions that we have to answer before we are sure that it works properly. And so SWOT, for the SWOT mission, it has been decided to spend quite a lot of time and energy to the validation, the prior validation and prior calibration of the measurements. And in this frame, there is a specific program to ensure this work of validation calibration. And so what I will present you now is what we are used to do for this work for the radar altimeters on board satellites, and what we plan to do, we have started to do, and we plan to do for the SWOT satellite. And also, a specific point about this is that it's also an opportunity for public science and what you call Ciência Cidadã, and which can be very interesting opportunity in Brazil, because it has been a very long time since we worked with Brazil in this work for calibration and validation of satellites. And then I think that together with official organizations such as CPRM, ANA, and universities and so on, it could be extended to more people. That's that's what I will just show you now. So, bon, Nicolas showed most of the same slides as I will. I apologize for this, but it is, I think it is worth insisting on this point. Just a small word to say that because I speak in English, I try to make the text on the slide in Portuguese. I hope I did not make too much mistakes. And in this case, I apologize. So this graph was already showed by Nicola, and it displays the number of discharge data that are available at GRDC. GRDC is important and emblematic because GRDC is a United Nations organization, and it is funded by United Nations to collect the global data, which means that any country can send its discharge or water level data to this database to make it available, publicly available for research, for planning, water use, and whatever you can imagine. And so the number of data has been regularly increased since the beginning of the creation of this organization up to the 70s. And after the 70s, for many different reasons, the number has started decrease. And as you can see, it has decreased much more rapidly than it was increasing before. And up to now, we are in a very dramatic situation, which is that the number of measurements that are collected by this organization is less than what it collected at the time of the First World War. Which means that, as Nicolas said, we have not the capability to properly monitor the continental water cycle using these publicly available measurements, which doesn't mean that these measurements do not exist. It just means that they are not made available for science, for students, for schools, for whoever who wants to look at the evolution of a basin. So, and this is not the same everywhere. This map shows that the global repartition of these measurements throughout the world, throughout the continents. And as you can see, the number of measurements, and in particular the age of the measurements, varies a lot from one place to the other, and even within a given country. As you can, for example, if we look at Brazil, we can see that some data can be very recent, but in other basins, such as the Tocantins Basin, as far as I can see, the data are very old. So we do not know why. Just maybe it's not a will of the country not to send them. It's just, well, they are not given to the international database. And of course, it is even worse in Africa or in Central Asia. In China, you have almost no data. And in, for example, in Russia, we know that some data should exist because we have old data, just we have no recent data. So this is just a fact that we need more information about the water cycle, and recent information. You see the time scale. If we want to study the climate, the time scale is about 30 years. We need to have the change in water level, the change in discharge over a time scale of about 30 years if we want to be able to say, okay, this is because of climate evolution, or this is just the year-to-year change. It's not a big matter. So, and these recent data are exactly what we miss. Okay, so how can the satellite help for this? I will go very briefly because Nicolas already said most of it. Just another view maybe of the way we can help. This map shows all the targets that have been implemented on board the Sentinel-3 satellites. Sentinel-3 satellites are satellites of the Copernicus constellation launched by Europe, okay, to monitor climate variables and others throughout the world, okay, in order to have the best possible knowledge about the physics and chemistry of the Earth. So these two satellites, Sentinel-3A and B, are similar satellites that are just flying two interleaved orbits, and one of their instruments is an altimeter. There are other instruments, but one of them is a nadir altimeter, working in SAR mode, but more or less the same way as the previous ones. And as you can see, it is tens of thousands targets that we could implement on board these satellites, which means that every time a satellite will pass right over one of these points, it will take a measurement. The
Recording in progress.
The satellite will not measure continuously as it was doing before. It will measure specifically when it is over one of these targets. And by this way, because we can send message to the satellite to say, okay, at that point, you have to be waiting for the echo at that moment and so on, because we have an a priori knowledge of the water level. This helps to improve dramatically the quality of the measurements, because the altimeter is really ready to receive the echo, and there is much less data loss on board the satellite. So just by the number on the spread of all the targets that we can have with a satellite, you can see that we can help to have more information, in particular over the basins that are poorly monitored with in situ measurements. So, in order to be more concrete, I would say, more. I chose to insist on basins that you probably know better, which is not so far from Fortaleza, where Marielle is, and which is a very important basin for Brazil, which is the San Francisco River, because it has a very important, it plays a very important part for agriculture, for energy, and for trying to bring water in an area of Brazil which is regularly lacking of water, which is Nordeste. So I took this place as an example for the rest of the presentation. And so this is the orbit of Sentinel-3. What you can see is that at any crossing of these green lines with the river course, you can take a measurement of the water level. You see, and so these points just highlight these crossings, and which means that with the satellite, which is currently flying, and it has been launched in 2016, so it has been flying now for 5 years, we have a pickup of the water level at all these green dots. The satellite is flying a 27-day orbit, which means that we have a measurement every 27 days. The second one, which is also flying now, it has been launched in 2018, is the Sentinel-3B, which is very similar, but as you can see, just the orbit is shifted with respect to the one of Sentinel-3A. But also, similarly, we have crossings with the river and its tributaries, and at each of these crossings, we can pick up a measurement of the water level. We have a third one, which is very important, which is Sentinel-6. Actually, Sentinel-6 is the last born of a long-lasting family, which is a Topek-Jason family, which used to be a CNES NASA program, but now it has turned to be more operational, and it has been included in the Copernicus constellation, because Copernicus constellation deals not with research satellite as it was for the Jason satellite, but deals with operational satellite, which also has a big advantage to offer a guarantee of the measurements. Okay, it's a much important program dedicated to guarantee the data. And so, because it is the last of this series, it is on the same orbit, which is a 10-day orbit. So we have much more measurements along the track, which for each of the crossing with the river, we have much more data, more or less 3 times more data. Of course, we have much less crossings because the satellite cannot at the same time come very frequently on the same place and sample as much places. So if we put all these places, what we call virtual stations, all together, you can see that we have a very good sampling of the river. Okay, but remember that all these samples will be taken at different places and at different days. And this, of course, specificity of a river is that the water level is changing every time and from one place to the other. So it's very helpful, of course, but it's not 100% satisfactory. We would like to have a better coverage in space and time. So that is one of the goals of the SWOT mission. So this, what I show now is more or less the same as what Nicolas showed, but I tried to focus on South America for today. And so I will just show you the coverage that SWOT will offer over South America and more specifically over Brazil. So this is the coverage that we will have on day one of a cycle. So the width of the lines is actual width with respect to scale, of course, actual width of the swath. Okay, and so you see for one day you will have more or less 4 tracks passing over South America. The second day you will have the same chain shifted westward. Okay, and so day 2, but you can see, okay, day 3. An important point is that you see, for example, over Argentina, that we are starting to have many crossovers. Crossovers are places where we have 2 samples during one cycle. Okay, one is with the ascending track from South Pole to North Pole, and the other measurement made by the descending track from North Pole to South Pole. And because we have large swaths, large area covered by each pass, we have each place will be sampled 2 times per cycle. So we will have a big amount of measurements and a big increase in the temporal sampling together with the spatial sampling. So if we go now for day 4, okay, you see that we are still improving the coverage. Day 5, well, I will not do all the 21 days. Let's shift to day 18. As you can see, we are very close to a full coverage. We have only a few places where we have only the ascending or descending tracks. These places are still waiting for the full coverage. Day 19, only 2 lines are missing the double measurement. Day 20, very few. On day 21, we have a full coverage of 2 measurements per cycle everywhere over the continent, and then every two measurements per cycle for any river larger than 100 meters all over the South American continent. And as you know, even much better than me, you have plenty of rivers larger than 100 meters wide in South America. So, as Nicolas explained again, because SWOT will be a game changer and will raise many technical questions, the first phase of the mission will be a phase dedicated to the validation of the data. In order to do this the best way, it has been decided by the space agencies to put SWOT on a specific orbit, which is a daily repetitive orbit, which means that we will have a very poor coverage, but along these tracks, the satellite will come every day. And as you can understand, if we want to make field measurement on the check at the data at a given place, it's much better that to have daily measurements to collect a lot of data in a very short time, let's say 2 months, instead of having to wait for 2 weeks, 3 weeks before we have the next measurement. So this is the coverage of this one-day orbit over South America. In the red box, I show all the places where we intend to conduct field work during this validation phase in South America. As you can see, 4 of them will be in Brazil, over San Francisco River. Here,
Recording stopped.
One over the Paraguay River here on the Pantanal swamps, which is also a very important goal for SWOT. Of course, the extension, the variability, the evolution of these wetlands. One will be over the central Amazon, also with, it will sample the Kuruai Várzea, which is very important place for biodiversity and so on. And the last one will be on the upper Negro River. One place will be in Colombia on the Meta River, which is a tributary of the Orinoco River. And last one will be on the Maroni River. Maroni River is the river marking the
Recording in
frontier,
progress.
the boundary between French Guiana and Suriname. So it's very interesting for us because we have a research center here in French Guiana, and also, of course, the space base for CNES in French Guiana. So having this one-day track passing over this river is very important because we are very close to the river itself, and we can collect many measurements very easily at this place. So coming back to the San Francisco River, the gray bands show the swath of the satellite during this one-day phase, this daily phase, and the dots, the color red dots, show as the same as the dots I showed previously for the, I would say, classical satellites, the Sentinel satellites. You can see that on the left band, we have a crossing of 2 satellites, which means that both Sentinel-3A in green and Sentinel-3B in yellow will take measurements almost at the same place. So we will have twice as much samples at this given place, which is just at the just downstream the Sobradinho lake. So it's a very interesting place. And on the right band, we have measurements for the 3 classical satellites, red for Sentinel-6, yellow for Sentinel-3B, and again, green for Sentinel-3A. And what you can see is that, so these 3 virtual stations will sample the swath, borders of the swath, and at the center of the swath for the yellow dot. So because we expect
Recording
that
stopped.
the error in the measurements we may
Recording in
change,
progress.
may be different from the center of the swath to the borders of the swath, just because of the change in angle and so on. It's very interesting to be able to follow, to monitor the change of water level at these different places. So what we plan to do is to install in situ measurements at these 4 locations, D1 on the left, under the left swath, and the 3 ones on the right swath. This way, we will be able to compare in situ measurements, classical altimetry measurements on the SWOT data. And of course, we will also, because it is for SWOT, we will also collect continuous measurements across the SWOT, and I will show this afterwards. So now I will show you a short video that was made by CPRM, because CPRM was we had a very long cooperation with CPRM for the monitoring of the satellites, and in particular for the classical altimetry satellites. So the advantage is that it is in Portuguese for our Brazilian attendees, and I think it's much better than my view graphs. So it's just a few minutes.
Stéphane, on n'a pas le son, donc peut-être que tu peux expliquer.
Ah, merde. Não tem som?
Pas de la vidéo,
Voilà.
mais...
Bon, so I try some tests, and if not, we will skip the video. Or I will just give some translation of what they say, because I know it. But okay, let me try some tests. Oh. Bon. Je suis désolé, ça a planté. Là, vous avez le son ou pas?
Non, je pense que le mieux, c'est que tu expliques, hein, ce sera plus simple en fait.
Ok.
On n'a pas l'image non plus d'ailleurs. Hein.
Vous n'avez pas l'image non plus?
Non.
Je ne sais plus quoi faire, moi. Et là? Là, vous avez l'image?
Oui, là, on voit ta présentation. Ok, là, c'est bon, on a l'image.
Et le son?
Non. Oui, c'est mieux que tu expliques. Hein.
Okay, so this video was taken by CPRM, okay, the agency in charge of collecting the water levels in Brazil. And so they explain the way we work in order to work together for the validation of the altimeters. So, well, just so we install GPS stations on the ground and on board the ship that you can see here. You can understand that when the ship is navigating, it is collecting water level measurements. These measurements are controlled by the ground station in differential mode, but specifically for the Amazon and for the large rivers, the ground station is also in place in order to control the crustal motion, because the ground is moving with the load of the water. So we have to take this into account when we want to compare to the satellite measurements. Well, this is just for fun, just to show how life is difficult on the boats. Well, okay, so good luck for you. You do not understand what I say. And so they are just showing that we install stations with GPS antenna, preview rain gauge, to have the full monitoring of the climate variables on the river. Well, that, so just talking about the explaining what we are doing and for which satellite it is, which is in this case Sentinel-3 satellite. It's on the Amazon River. Still no sound? You have no sound? Marielle?
On l'entend, mais très très bas. Toi, on t'entend très bien, mais le son de la vidéo, on l'entend très très bas.
So this is an important image. This is, you see, so let me come back to it. Just let me wait for next. So this is typically the gauge in the Amazon River, but in many places in Brazil or whatever the country, which are used to collect water level measurements. And as you can see, so it's a series of wooden sticks. Each one has a rule where someone will read the measurement, the value daily. And as you can imagine, installing such a station is quite a big work, because of course here, for example, the river is moving for 15 meters between the low waters. It's changing for 15 meters between the low waters and the high level waters. So you need many bars like this to sample the water level from the very lowest to the highest. And you need to hire a guy to come daily and check at the water level and read the measurement. Well, so maybe we could go. Well, she's just explaining same as what I explained to you. Well, I'm very sorry if you have no. Can you hear him or not? Marielle, can you hear him?
C'est très bas. En fait, quelqu'un a fait des suggestions. Apparemment, quand tu fais screen sharing, tu as une option pour partager le son, en fait. Mais Slee t'a envoyé un message détaillé. Mais bon, je pense que le mieux, c'est de continuer comme ça. Ouais.
Bon, moi, je veux bien... je sais pas comment on fait ça, partager le son. Plus, peut-être. Partager l'audio. Ah! So, I try again. Là, vous entendez?
Yes, yes, bravo!
Bon, so... Bon, we have time. So.
Nossa aventura começa no porto de Manaus. Nosso destino, o coração da floresta amazônica. A missão, montar 2 estações de monitoramento no rio Amazonas. A expedição era formada por técnicos da CPRM e pesquisadores da Comunidade Europeia. A bordo do barco Samara Lopes, descemos o rio Amazonas. Após 6 horas de navegação, atracamos na margem esquerda do rio, próximo ao povoado de Bom Sucesso. No local, estabelecemos a base de operação da expedição, que busca decifrar a dinâmica fluvial do rio Amazonas. Os primeiros dias foram dedicados à montagem das réguas de medição do nível do rio. Trabalho árduo, realizado debaixo de um sol escaldante, de chuvas tropicais. areia, cimento, pedras, madeiras e equipamentos foram transportados nas costas do barco por cerca de 1 quilômetro até o alto de um morro, onde as estações foram montadas. Esse trabalho de formiguinha, subindo e descendo o morro, exigiu esforço físico enorme da equipe. O barulho de furadeiras e marteladas só parava ao entardecer, quando a equipe se recolhia no barco para jantar e dormir em redes improvisadas no convés. O pesquisador francês Stéphane Calment explica que a pesquisa busca estabelecer uma nova metodologia para a medição de grandes rios no mundo, com o apoio de satélites.
E aqui tem uma boa sorte de ter cruzamento entre 3 satélites. Um satélite antigo, que está voando agora mesmo, que se chama o Saral, e mais 2 outros satélites que vão ser lançados o ano próximo, que se chamam o Sentinel-3, que são satélites de um projeto muito grande da Europa. Então, o bom sorte é que esses 2 novos satélites vão fazer um cruzamento exatamente no rio abaixo daqui. E o trabalho que a gente faz aqui vai servir para todas as bacias do mundo, que seja o Congo, na África, o Ganges, na Índia, o Yangtze na China, pouco importa. Os resultados que a gente tem aqui para o trabalho de pesquisa, para avaliar os dados, vai servir para a população geral sobre essa questão de monitoramento do recurso hídrico.
A iniciativa é fruto de uma parceria entre a CPRM, o Instituto Francês IRD e a Universidade Estadual do Amazonas.
Essa parceria é extremamente importante porque é uma parceria de uma academia com uma instituição operacional. Nós temos um GPS que vai medir o quê? Vai medir a variação da crosta, porque a crosta também ela varia em função da carga de água, quando sobe e desce o nível de água do rio. E nós temos uma estação meteorológica também instalada, para quê? Para verificar a correção desse sinal do satélite quando ele atravessa a atmosfera.
A CPRM vai participar desse grupo, faz parte o IRD, a UEA, e nós todos juntos vamos trabalhar nesse sentido, para ajudar no monitoramento da bacia amazônica. Está dando um passo no futuro, que é o trabalho de o uso de sensoriamento remoto na Amazônia, né? Não há como se fazer monitoramento hidrológico na Amazônia sem sensoriamento remoto. Sensoriamento remoto vai ser no futuro o grande instrumento para que a gente possa fazer o monitoramento hidrológico da bacia amazônica.
O especialista grego em calibração de satélites altimétricos Stelios Mertikas diz que conhecer a Amazônia era um sonho de infância e que veio conhecer o trabalho da CPRM para comparar ao que ele realiza em seu país.
We've been calibrating satellite altimeters for about 15 years in Greece, and we would like to see if and how the calibration is going to be done in the Amazon.
Alicia Morim conhece os rios da Amazônia como poucos. É uma verdadeira Amazonas da mitologia grega, que há 16 anos percorre os rios da região, coletando dados e fazendo a manutenção das estações que a CPRM opera na Amazônia.
Enquanto o congestionamento no eixo sul-sudeste é de carros, caminhões, na Amazônia nosso congestionamento é esse que está passando aqui atrás. Balsas, barcos, essa é a nossa estrada, os rios da Amazônia.
O orgulho em contribuir com a ciência e participar de uma pesquisa científica que vai produzir conhecimento para ajudar a população de ribeirinhos e das grandes cidades que vivem às margens do Amazonas torna o trabalho gratificante, diz o auxiliar de campo Marcos Barreto.
Nosso trabalho em si, eu acho que todo trabalho tem sua utilidade, né? O nosso em si, ele é muito bom para determinar eventos como as cheias, né? Onde você pode preparar os ribeirinhos, onde tem muitos locais que são alagados, eles podem ter essa previsão com um pouco de antecedência.
Ele compara seu trabalho ao de formiguinha, mas que no final faz a diferença.
Define aí seu trabalho para mim em 2 palavras.
O trabalho ele é desafiador e gratificante.
Ao final da expedição, voltamos para casa com a sensação do dever cumprido. E o Amazonas nos brinda com um belo pôr do sol, agradecendo a nossa visita e nos convidando para voltar outras vezes.
Recording in progress.
So, sorry for the small technical problems. And as I said, and it was explained in depth by Nicolas, this is not enough now because we expect SWOT to make continuous measurements of the river. And then what we did and what I showed in the previous video was dedicated to make punctual measurement, comparison between punctual measurements with the punctual measurements of the satellite. Now, we want to make on the ground continuous measurements of the water level because the satellite will provide this kind of information. So we have to think differently, and we developed a new instrument to collect these kind of measurements. It was partly done on the previously, as you could see, we installed GPS. I don't know if you noticed that on the roof of the boat. It was to start doing this kind of continuous measurements, because as long as the boat was traveling, we could collect the change in the height of the water level owing to this station on the boat. But as it will be explained in the next video, this was not fully satisfactory because the boat has its own motions, own movements, and so we had a merge between the change in water level and the change in the boat itself. Also, we try to come to the last point, which is to involve more people in particular to make this an opportunity for education. And so we conducted a program together with French school and Guyana, French Guyana schools to involve students in our project, in our fieldwork. This program was supposed to have 3 steps. First step was just for a start, I would say, in the small river, which named Garonne River, which is flowing very close to Toulouse, in south of France. The second step was supposed to come on a middle-sized river, which is the Maroni River here in French Guyana. And the last step was supposed to be on the Negro River. All of these rivers being places where we will have an overpass of the one-day orbit of SWOT. So this is again a small movie. I'm very sorry the text is in French. I understand that the translator cannot translate French to Spanish or to Portuguese. So I will give you some comments during the vidéo. Just
Recording in progress.
Pour commencer à
the guy speaking is a
donc
French
une zone d'études hydraulique et hydrologique un peu particulière. C'est un site de calibration pour le satellite SWOT Et donc, on est venu ici faire des mesures en vue d'établir des modélisations hydrauliques précises, caractériser le cours d'eau afin de pouvoir donner un retour et calibrer les mesures du futur satellite. On a une collaboration depuis plusieurs années avec certains des collègues présents sur la manip. Notre travail a consisté, celui sur lequel j'ai été impliqué pendant cette campagne de mesures, des mesures de débit.
So what he says is that together with measurements, we come back to it, we are doing some discharge measurements, bathymetric measurements, in order to have the full information about the river bed,
de réseaux en tresse,
the flow,
de son, de bathymétrie, donc des rapides qu'on a passés en pirogue. On s'est intéressé à effectuer des mesures assez fines et distribuées des flux dans cette zone, en vue de pouvoir fabriquer une modélisation avec une bonne signification physique. Et ces mesures-là serviront notamment indirectement ensuite à utiliser des données satellitaires, donc des données satellitaires altimétriques plus anciennes, actuelles, et celles du
before the launch is to collect as much measurements as possible because we have no guarantee on the timing of the measurement of the launch.
Des dérives de capteurs GPS ou à la surface de l'écroulement.
Le système que vous voyez derrière vous, c'est le système Calna-Géo, c'est une nappe de calibration géodésique qui sert à mesurer la surface libre de l'eau. L'originalité de ce système, c'est que avant on mesurait, on utilisait des antennes GPS montées sur des bateaux et on mesurait à la fois le niveau libre de l'eau, mais superposé à ceci, on mesurait les mouvements du bateau. Et donc la mesure se trouvait entachée d'un biais. Donc l'originalité de ce système, c'est qu'en fait on traîne derrière un navire et le système est juste à la surface de l'eau et suit parfaitement ces mouvements sans superposer d'autres mouvements. Et donc on a exactement la surface libre de l'eau grâce aux signaux de satellite GPS qu'on capte.
Recording stopped.
Quantité d'eau qui sont transportées donc dans les bassins versants et le fleuve Maroni étant le premier grand bassin versant de la Guyane, il y a un intérêt fort.
Working on chemistry, mostly
on a également une deuxième mission, c'est la mission d'éducation à l'environnement.
In the river together with the flow.
Pour solliciter des
and so she did a lot for training the students
à cette mission, donc dans l'objectif en fait de leur
participate to collect this is biological
et leur expliquer en fait quel est l'intérêt de suivre les quantités d'eau qui sont transportées, également suivre la qualité de l'eau. L'absurdité est souvent entraînée par de l'érosion,
giving information, scientific information to young people about all the aspects of the water cycle, either physics quantity or the chemical quantity.
Et on a fait donc le consacre, le Maroni est encore vraiment très orpaillé, avec des valeurs de turbidité à plus de 50
So she's just saying that what we discovered is that the pollution in this river is much higher than people were thinking about, and in particular because of gold mining. So the activity of gold mining on this on the upper part of this river is such that we have a big pollution. So at the end, just to summarize this this experiment that we had, and to give you an idea of what we are conducting in terms of including young people in to the scientific activity. So this is just a photo of the group, and the group included 15 young people from either from France, main France, and French Guiana, but we also have their professors. Here are the ladies. We had researchers, including one guy from GPL, NASA, from US, who accepted to come very kindly. And we had a colleague from CPRM, Brazilian colleague, and I think she is hidden here, Escondida aquí. And so we had also researchers from France and French Guiana. So more or less 30 people. And if we can summarize in a few words,
recording in progress.
The students learn during that visit. Okay, they learn to before they come, they try to develop their own sensors for water level or for chemistry. When they arrived, their first task was to install some of their sensors, and they could learn that it's much more complicated to do when you're on the field work out of the lab. It's what you scheduled on the lab may be very different from the reality on the field. So they participated to collect measurements of physics, which is here the leveling of their sensor. Leveling means to have the absolute height of their sensor. So their sensor is in the tube that you can see on the foreground here, which is a sensor collecting the water pressure. And so because it is in the tube, we cannot access directly to the sensor to ensure its position into the underwater. So we, together with the measurements collected by the sensor, we made measurements with the GPS, which also measure the height of the water level. And by combining these two measurements, we can transfer just the local measurements of their sensor into absolute measurements that can be compared to the satellite. So they also benefited of classes given by all the scientists participating to the fieldwork, so our Brazilian colleague here from CPRM, myself, and Ernesto, who is from GPL. So that just to show that how they participated to collect the water samples, and after they made the test, the analysis of these samples in order to extract the information about mercury, arsenic, and other very unpleasant materials that you can find in this river because of gold mining. Maybe the most important, they learned to survive in very difficult situation. Our life very different from what they have in their city. Whatever it is for main France or even students from Cayenne, they are not very used to the field. And
recording
they learn
stopped.
Also to be always of good temper.
Recording in progress.
Which is very, very important in this kind of situation. So this fieldwork was here on the Maroni River. It was in 2019, and it was expected that in 2020, we do the same on the Upper Negro River. But because of COVID, of course, this was cancelled. And so we will see if we can do the same. Another one in maybe in Central Amazon here next year. And so we are entering into discussion with CPRM to see if we could organize something here next year. And so we are very open to participation if some group want to participate. We can, discussion is very open. That's it. Thank you. I'm done.
Yay! Obrigado. Thank you, Stéphane. So we know that we can dream with a satellite, but also with in situ. So it's very important to do both. We are convinced. We have a question. Well, we have a lot of questions actually. One from Pablo Santos. I don't know if you see them. Do you see the chat? Otherwise, I can read it to you. Poderia explicar novamente qual o papel daquele dispositivo que estava amarrado na parte de trás do barco, coletando informações de GPS?
Okay, so maybe I should show again. I can stop the video. Okay, you see my presentation again? Marielle?
Yes.
Okay, you see it? Can you confirm that you see it?
Yes, we see it. It's not in presentation mode. Yeah, it is in presentation mode. Yeah.
So I just try to find the right maybe this one. It's not the best one, but maybe the very first one actually was better. Here, here you can see that we have one here. Well, I'm sorry, it's not a best view, but we installed some GPS stations and we were continuously recording the GPS signals. Okay, and as you can understand, from Manaus to the place where we had the work, we could see the change in water level experienced by the boat because of this recording of the measurements. Is it the good answer to the good question? Did I understand the question properly? Okay. Ho notei Alderlene Brito che falou que quer participar na campanha. Então, é só falar com a Marielle. Vamos ver o que podemos fazer. Com prazer. So, next question is, what kind of height conversion do you apply to the ellipsoidal height derived from the GNSS survey, or the calibration is perfect directly with ellipsoidal height? So, this last question is about referencing the measurements. Actually, the satellite altimetry measurements are also natively referred to ellipsoidal heights, okay, because they are based on orbits computed from GNSS sensors. Whatever they are, the Doris sensor, the GPS, the Galileo's instruments, and so on, all provide values referred to the WGS 84 ellipsoid. Okay, so which is so what we collect using GPS sensors on the ground is directly can be directly compared to the ultimate satellite measurements. Was it clear? Actually, if you want, you can also compare to other reference such as geoid model. If you want to have the physical slope of the river and so on. Just the point is to apply to be sure that both your satellite measurements and the measurements you collected in situ do refer to the same reference, whatever it is purely geometric, the ellipsoid, or gravity included reference. But it's a very good question. It's a very important point. People have to be very careful about this. I agree.
Olá, Stefano. Stephanie, aqui é o Geraldo. Stephanie.
Yes.
Parabéns aí pela sua apresentação. Eu gostaria de saber se é possível ter outros sites de validação aqui na região semiárida aqui do Brasil.
I showed that the validation work, which is planned unfunded, very sorry for that, but money is a key point, with CNES, the French Space Agency, on support of the local agencies such as CPRM for Brazil, okay? And during the calibration phase. After this calibration phase, we will have the scientific phase, which will last 4 years. Of course, everyone who is interested in doing some comparison between the satellite measurements on in-situ measurements at the place where they live or where they are working on can do it. So, on this for sure will participate to the continuous validation of the measurements provided by the satellite. All along is life. We need that this kind of measurements is done. This was not the scope of my presentation, but for sure, we will see if we can have a worldwide project that will coordinate this kind of work done by local people everywhere, every river they have in their neighborhood, and who would be interested in collecting ground measurements that can be compared to the satellite measurements. I just remind that the satellite measurements will be available for free to anybody. So any group, whatever it is, a school, students, and so on, or even the technical services of municipio or whatever, can collect the satellite measurements, and if they want, can organize their local collection of in-situ measurements to compare with. This will be very open. The point is always how to fund it. That's it. Did I answer properly your question?
Yes, thank you very much.
So there was a question about the rain.
Recording stopped. Recording in progress.
So I'm not sure I understand fully the Portuguese. Levar em conta. I don't know what do you mean by levar em conta. If you mean by the delay that the rain may influence the radar pulses, yes, we know that this is a point, and so the rain will be followed by, but this is at the level of the space agencies using climate models, meteorological models to check for the rain during the pass of the satellite. We expect that it will affect only for a few % of measurements that may be lost because of the rainfall, just at the time of the satellite passing. And if it's just a question of delays, well, we have the global models for that. If not, if it is just about SWOT itself, SWOT is not supposed to provide information about the rain.
Okay, thank you very much, Stephanie, for presentation and collaboration in this workshop. And now we will call the next speaker.
Thank you. Obrigado a todos.
Ok. Alfredo Ribeiro, lá da Universidade Federal de Pernambuco. Bem-vindo aqui, Alfredo, ao workshop. Ele vai falar sobre o monitoramento de pequenos reservatórios no Nordeste brasileiro utilizando a altimetria. Alfredo, a palavra é sua.
Ok, obrigado. Agradeço o convite e a oportunidade de participar do workshop. Então, Stefane, acho que você poderia... Stefane? O teu vídeo ainda está compartilhado. Ok, obrigado. Então, sou da Universidade Federal de Pernambuco, Departamento de Engenharia Civil. aqui, digamos, é um esforço que estamos fazendo, né, no sentido de realizar estudos em reservatórios do semiárido do Nordeste.
Alfredo, you're not sharing your presentation as a presentation.
Não?
I think you have to go in presentation mode.
Sorry. And now?
No. No. I think you have to press the little button on the.
It's strange because for me there is a message saying that my screen is sharing.
Yes, you're sharing the presentation, but it's not in presentation mode. I think you have
presentation mode.
Yeah. Okay. Yeah. If you press
like
that,
this?
that will be good. Yeah.
Okay. Sorry. Okay. And isso aqui é um esforço, como eu dizia, de estudarmos.
It's still not doing it. Maybe you have
Not doing?
Yeah. No, you have to press again, maybe.
No.
Yes. Perfect. Thank you.
But I can't go forward. It's okay now?
Perfect.
Yes.
Ok. Bem, eu entendo que isso aqui pode ser alguns exemplos de aplicações que podemos ter futuramente quando os dados do SWOT estiverem disponíveis, né? Vou mostrar aqui duas aplicações que foram realizadas com as missões que estão em operação atualmente, mas que podem servir como exemplo para futuras aplicações com os dados do SWOT. Em primeiro, um panorama, né, do que a gente aqui vai considerar como pequenos reservatórios ou grandes reservatórios. Pode haver uma grande variedade de classificações. Isso aqui eu obtive de essas publicações que são mostradas aqui, mas, como eu disse, você pode ter outras classificações, né? Menor, seria um pequeno reservatório, reservatórios com capacidade de armazenamento menor do que 1 milhão de metro cúbico. Por outro lado, tem a Comissão Internacional de Grandes Barragens, que sugere aqui um valor de 3 milhões para grandes reservatórios. E nesse meio, entre 1 e 3 milhões, a gente bem consideraria aí os reservatórios de porte médio. Ainda, se pegarmos só os pequenos reservatórios, LIB e colaboradores em 2005 ainda faz uma outra divisão, né, em 3 categorias, que vai variar aí entre 1 e 3 hectares, 3 e 10 e 10 e 50 hectares. Isso aqui é muito mais para a gente ter só uma ideia de escala e da possibilidade de classificação dentro dessas dimensões de reservatórios. Lá no mais adiante, eu vou mostrar que, para aquilo que a gente está trabalhando atualmente, né, com Altimetria por satélite, certamente o que é pequeno para altimetria por satélite não se enquadra nessa classificação. Então, o que é pequeno para uma aplicação pode não ser pequeno para outra aplicação. Isso pode ser discutido posteriormente e, quem sabe, até se pensar em que tipo de classificação pode ser feita quando se fala em altimetria por satélite. Algumas informações sobre os reservatórios na região semiárida e no Nordeste. Existe um trabalho da Agência Nacional de Águas que fez a vetorização dos corpos d'água, isso em nível do Brasil, né, nível nacional. Se a gente pega esses corpos d'água para o Nordeste, a gente vai ter em torno de 27.400 reservatórios, sendo que em torno de 98% com superfície menor ou igual a 1 km². Então, uma grande proporção desses reservatórios são de pequeno porte, mas se considerarmos em termos de volume, né, a grande participação em termos de volume e de capacidade de armazenamento são dos grandes reservatórios. Em termos de uso, os principais usos desses reservatórios são para abastecimento doméstico, criação animal, irrigação, isso para unidades familiares, né, em zonas rurais, e em comunidades difusas e pequenas e difusas comunidades espalhadas no semiárido do Brasil. Com relação aos impactos desses reservatórios, temos aqui alguns trabalhos realizados no Ceará, inclusive, por exemplo, na bacia do rio Jaguaribe, que se estimou que os pequenos e médios reservatórios podem reter aproximadamente 50% do sedimento que é produzido nas bacias de contribuição. Isso, por um lado, pode ser positivo, na medida em que esse sedimento não vai chegar nos grandes reservatórios, né? E isso não vai, digamos, impactar a capacidade de armazenamento dos reservatórios de grande porte. Por outro lado, pode ter um impacto negativo no que se refere a favorecer o processo de evaporação da água, uma vez que ela está retida ali no reservatório. Isso pode alcançar em torno de 30% do volume de água que entra no reservatório. Bem, como eu falei, são dois trabalhos que eu vou mostrar aqui. O primeiro deles diz respeito à altimetria por satélite em pequenos reservatórios no semiárido brasileiro. Esse trabalho foi desenvolvido em parceria com pesquisadores do Instituto de Geodésia da Universidade de Stuttgart, na Alemanha, e com um colega do Serviço Geológico do Brasil, em Recife. O objetivo aqui foi validar as séries de nível da água em reservatórios do semiárido do Nordeste, no caso, utilizando, validar dados, né, dos satélites Ensat, Saral, Sentinel-3A, Sentinel-3B, JSON-2 e 3, inclusive já foram, né, mencionados nas palestras anteriores. Diante dessa validação que é feita, né, digamos, se a gente tem alguma segurança a respeito da qualidade do dado, a gente pode partir para aplicações secundárias, né, objetivos mais específicos, como, por exemplo, a estimativa do volume armazenado a partir da estimativa do nível da água no reservatório. E ainda um segundo objetivo foi avaliar a influência dos aspectos ambientais sobre a qualidade do dado que é gerado por esses satélites. Aqui tem a área de estudo, né, o Nordeste do Brasil. Foram 20 reservatórios que foram estudados. Aqui as estrelas na cor preta são reservatórios em que se fez apenas a avaliação do nível da água. E os triângulos em cinza são reservatórios que, além do nível da água, foi feita também a avaliação do volume. Aqui os períodos, né, de dados para cada um dos satélites. Os satélites Sentinel 3A e 3B são mais recentes, né, e em função disso, tem aí uma quantidade de dados menor em comparação com as outras missões. Aqui a gente consegue dar uma olhada na variabilidade, né, de dimensões desses reservatórios. Então, a gente pode variar aqui de em torno de 4 quilômetros quadrados de área superficial, até 67 quilômetros quadrados de área superficial. Tomando aquela classificação lá do início, certamente esses reservatórios não poderiam ser considerados naquela classificação como pequenos. Mas reforço a necessidade de talvez identificar o que seria um corpo d'água considerado pequeno para ser tratado no âmbito de uma aplicação com dados de satélite altímetro. Aqui, nessa coluna, a gente tem a variação do nível da água nesses reservatórios. A menor variação que tem é de 7 metros, mas, em alguns casos, pode chegar até 27 metros de variação, né, entre os períodos de águas baixas até a capacidade máxima de armazenamento do reservatório. E para cada reservatório indicado aqui é mostrado a missão que tem tracking, né, os tracks que passam sobre os reservatórios de cada uma das missões. Em poucos casos houve a situação de ter mais de um satélite passando sobre o reservatório. Acho que foram 4 casos com essa situação. Os dados medidos in situ, medidos nas estações in situ, foram obtidos do sistema mantido pela Agência Nacional de Águas, o sistema de acompanhamento de reservatórios. Esse sistema mantém atualizado, né, os dados de nível e armazenamento em reservatórios que cobrem todo o território do Brasil, mas não todos, né, são aqueles reservatórios mais importantes e onde há, de fato, o monitoramento. Então, todos os dados que foram utilizados para comparação com os dados dos satélites vieram dessa base. Para o cálculo do volume no reservatório, é necessário que se tenha o que a gente chama de curvas cota área-volume ou curvas profundidade área-volume. Por meio dessas curvas, né, dado como entrada o nível da água, a gente pode obter o volume correspondente no reservatório. Então, isso estava disponível, né, daquele conjunto de 20 reservatórios, em 7 deles são aqui, tem 2, 4, 6, 7, possuem essas curvas atualizadas, né, com dados obtidos a partir de batimetria realizada recentemente, o que permite fazer esse cálculo do volume, tendo como entrada o nível da água. E, bem, aí nesse caso, a curva é a mesma, mas a forma de obtenção dos volumes são distintas, elas vão diferir, porque a entrada do nível da água é diferente, né? Aqui a gente vai entrar com o nível da água a partir da estação, em solo, e o nível da água medido pelo satélite. Temos o resultado que essa tabela tenta resumir os resultados que foram obtidos, né, nos 20 reservatórios. Importante destacar que em algumas situações, né, o ciclo do satélite, a passagem do satélite, resultou em um dado que não foi possível de ser aproveitado, por 2 motivos. Ele simplesmente não foi processado, né, a qualidade do dado não era boa o suficiente para ser processado, ou então ele foi processado, mas gerava um valor que estava fora do padrão esperado para aquele reservatório. Isso significa excessivamente alto ou um valor excessivamente baixo. O fato é que essas 2 situações aqui, elas são consideradas como um ciclo não processado. Então, ele não vai entrar no cálculo do RMSE. No cálculo do RMSE entra apenas aqueles ciclos que foram efetivamente processados, e os valores desses ciclos, né, a quantidade de ciclos aparece aqui nessa coluna. Assim, em resumo, esse aqui é o resultado que se obtém, né, em termos estatísticos, né, a estatística RMSE, que é bastante empregada para esse tipo de avaliação. A comparação que é feita desses resultados com outros trabalhos mostra que os resultados obtidos nos reservatórios do Nordeste, eles possuem qualidade compatível com outros trabalhos realizados em outros locais do planeta. Essa comparação se procurou fazer com corpos d'água que tivessem características semelhantes, principalmente em termos de dimensão, né? Mesmo que fosse um rio, né, além de reservatórios, procuramos trabalhos que tenham utilizado corpos d'água com dimensões semelhantes às dimensões dos reservatórios tratados aqui. E, como eu falei, os resultados são compatíveis, a qualidade é compatível e, em alguns casos, até melhor do que alguns trabalhos que são disponíveis na literatura. Aqui é o resultado em termos gráficos. Separei aqui apenas 4 reservatórios. Em todos os gráficos, esses círculos na cor preta representam o dado da estação e os círculos coloridos representam os dados dos satélites. Importante dizer que esses dados que estão aqui dos satélites, eles foram corrigidos, né? Porque em alguns reservatórios, por exemplo, não há referencial altimétrico, então não é possível fazer comparação com o dado, diretamente com o dado que vem do satélite. Mas aí existe uma diferença sistemática entre o dado do satélite e o dado da estação, é possível calcular essa diferença sistemática e aplicar essa diferença sobre o dado do satélite. Ao fazer isso, é possível atribuir, né, uma correção desse erro sistemático, e o resultado é essa comparação que é mostrada aqui nos gráficos. Com relação ao cálculo do volume, aqui tem 4 dos 7 reservatórios que foram avaliados. Novamente, a cor preta é o volume medido a partir do nível da água da estação, e em vermelho o volume estimado a partir do nível medido pelo satélite. Percebeu uma leve tendência de subestimação do volume, né? O volume calculado pelo satélite, ele teve uma leve tendência de subestimação. É como mostrado aqui, em 5 dos 7 reservatórios, o volume foi menor do que o volume calculado pelo nível da estação. Mas, de uma forma geral, esse erro de volume, a gente percebe aqui por esses números, que ficou com uma qualidade bastante razoável. O que mostra do potencial de utilização do dado do satélite para o monitoramento desses reservatórios, não só do nível, mas também para o volume, né? Que, no fim, é o que tem mais interesse, assim, para a gestão dos recursos hídricos, né? Na ponta do gestor que vai utilizar o dado, é importante que se saiba qual o volume armazenado no reservatório, volume de água disponível. Sobre os aspectos ambientais que podem interferir, né, podem impactar a qualidade do dado obtido pelo satélite, que estão destacados 3 aspectos. O primeiro deles diz respeito à variabilidade sazonal do nível da água nos reservatórios. Isso é muito influenciado pela própria característica do clima da região. A precipitação no semiárido do Nordeste se concentra em torno de 4 meses do ano, e em 8 meses se tem o período de estiagem com a ausência de precipitação. Então, essa característica climática leva a uma grande variabilidade sazonal, tanto hidrológica como, por consequência, também nos reservatórios. Depois teve situações em que a largura do corpo d'água na passagem do satélite era muito pequena, e isso comprometeu a obtenção dos dados em alguns casos. E, por último, as características topográficas próximas à borda do lago. Como exemplo, né, dessas 3 situações, pode mostrar aqui no primeiro caso a variabilidade sazonal. Não sei se vocês conseguem ver aí, mas aqui está nessa linha vermelha o track do satélite, né? A posição onde o satélite está passando. E aqui desse lado a mesma posição do track, e em azul o limite, né? A borda do lago. Só que, nesse caso aqui, numa situação completamente seco. Aqui ele está cheio em outubro de 2012, né, uma situação bastante favorável para a obtenção do dado pelo satélite. E aqui é um outro extremo em que o lago está completamente vazio. E isso ocorreu de forma mais drástica, porque em 2012, o semiárido do Nordeste passou, iniciou um período de seca prolongada, com precipitações abaixo da média histórica, e durou por cerca de 5, 6 anos. Então, começou em 2012 e se estendeu até 2017, 2018. Então, nessa situação, vai levar a um impacto, a um prejuízo na obtenção do dado. E pelo gráfico, a gente pode ver que o dado obtido pelo satélite acompanha muito bem aquele que é medido pela estação, mas chega um momento em que o nível da água é tão baixo que já não existe praticamente o que medir ali no reservatório. E aí a gente vai ter uma situação, como a que eu mencionei anteriormente, em que pode até haver o processamento do dado, mas esse dado ele não condiz, ele não reflete, de fato, o padrão que se espera para o nível da água no reservatório. Então, esse é o primeiro aspecto ambiental, eu estou chamando aqui de aspecto ambiental, que é o que está relacionado com a sazonalidade, do impacto da sazonalidade sobre o monitoramento. No segundo caso, isso aqui é um reservatório que o satélite passa numa posição que não é muito favorável. Esse aqui é um reservatório bastante extenso, bastante alongado. O ideal aqui seria que a passagem do satélite fosse mais na parte central do lago, em que você teria ali uma largura maior, que pudesse ser melhor aproveitada para a obtenção do dado. Aqui é um exemplo, ele está o satélite na entrada do reservatório. Essa largura não é suficiente, mas teve outros exemplos em que houve a obtenção do dado. Por exemplo, passando em um afluente, um tributário de menor porte, que pode ser considerado como ainda parte do reservatório, mas, em função dessa característica, não é possível obter o dado. E por último, aquele terceiro aspecto que foi identificado, diz respeito à topografia da vizinhança, das proximidades do reservatório. Aqui mostra o perfil transversal do lago. Então, o lago está aqui. Então, esse aqui seria o perfil transversal, que coincide com a trajetória do satélite. Em situações que há uma diferença de nível muito grande, de elevação entre o terreno e o nível da água de forma muito abrupta, isso pode trazer prejuízo para o sensor identificar onde está a água e o retorno da informação para o satélite, para o sensor, deteriorado. Nesse trabalho de Bianca Maria, realizado em rios da França, foi identificado essa característica, de como essa característica da topografia pode influenciar o resultado final. E lá eles chegaram nesses valores que, entre si, essa diferença de nível, daqui da topografia até o nível da água, se tiver ali entre 50 e 100 metros, ou se a declividade for de 80 metros por quilômetro, isso pode resultar em prejuízo. Nesse caso, nesses dois casos, tivemos essa diferença de 50 metros, que está dentro dessa faixa, né, que foi identificada pelos autores, e nesse outro também houve problemas de obtenção do dado. E aí, nesse caso aqui, não havia nenhuma das outras situações, não era o caso de uma largura pequena, nenhum caso de variação em decorrência da sazonalidade, mas a gente identificou essa diferença de cota, que não está dentro dessa faixa, mas que pode ter influenciado o resultado final. Uma informação importante é que esse perfil ele foi construído de forma relativamente simplificada, porque esse aqui é um dado do modelo digital de elevação do SRTM. Ele possui a resolução de 30 metros e a precisão vertical dele pode não ser a melhor, né, a mais apropriada para essa análise que precisa ser feita para essa situação. Quer dizer, se a gente quer, de fato, verificar se a topografia é que está influenciando na qualidade do dado, é necessário que se utilize aqui uma informação mais precisa para que se tenha valores mais próximos da realidade e daí tirar as conclusões. Bem, então, isso se refere ao primeiro trabalho, que diz respeito à utilização das missões de altimetria por satélite para a obtenção do nível da água e, posteriormente, o volume em pequenos reservatórios no Nordeste. Isso foi um desafio, porque assim, a gente não tinha ideia da viabilidade disso, né? Existem muitos trabalhos que foram realizados em grandes rios, em grandes lagos, utilizando esse mesmo conjunto de dados, mas em função dessa característica de se tratar de grandes corpos d'água, é de se esperar que haja uma boa resposta do satélite. Mas nesse caso aqui, a gente tinha essa dúvida, e ao longo do trabalho acabaram aparecendo essas dificuldades, né, em função das características ambientais da região, mas que serve como uma primeira ideia, uma primeira aproximação do que a gente pode realizar com esses dados no semiárido do Nordeste. Eu achei que foi bem interessante e assim, acima da expectativa que eu tinha antes de realizar essa validação. Bem, o segundo trabalho, ele diferencia um pouco do primeiro. Aqui a ideia é fazer uma caracterização geométrica de reservatórios a partir de dados altimétricos. Esse dado altimétrico pode ser tanto o dado medido na estação, como pode ser também um dado medido por satélite. E foi esse o caso aqui. A partir do dado de satélite se faz uma associação com imagens óticas para poder fazer a caracterização geométrica de reservatórios. Isso é um trabalho que foi conduzido pelo doutorando José Bacalhau, um trabalho de doutorado do programa de Engenharia Civil aqui da UFPE, em parceria com colegas do CNES, Jean-François e Muriel, e do Serviço Geológico do Brasil, Daniel Moreira. Esse trabalho foi submetido recentemente Nossa expectativa é que possa ser publicado em breve. Então, o objetivo foi explorar o cálculo explorar a potencialidade, né, de utilização do dado do ICESat-2, assim, do satélite ICESat-2, em combinação com imagens ópticas para o cálculo da batimetria de reservatórios. Aqui, nesse caso, a gente acabou envolvendo muito mais grande reservatório e reservatório de porte médio. São esses dois reservatórios que foram utilizados no estudo. Esse aqui é o lago de
Recording in progress.
E definitivamente, independente da classificação que se adote, ele não pode ser considerado um pequeno reservatório. Em qualquer classificação, ele é um grande reservatório. E o Sul da Cruz é um reservatório de médio porte. Ele estava na relação dos 20 reservatórios do estudo anterior, possui em torno de 50 km² de extensão na sua cota máxima, e 450 milhões de metros cúbicos de capacidade máxima. Ambos estão na bacia do Rio São Francisco, na mesma bacia que Stefani mostrou na apresentação anterior. Aqui eu vou mostrar só o resultado que foi obtido com o Poço da Cruz, porque nesse caso de Poço da Cruz foi utilizado apenas o satélite ICESat-2, né, o dado do ICESat-2. O primeiro de tudo é fazer a classificação da água, por isso que de um lado se utiliza o dado altimétrico, mas por outro lado a necessidade também da imagem, né, da disponibilidade da imagem. Com essa imagem são aplicados índices espectrais, NDWI, o MNDWI, que permitem, né, a identificação do que é água. Aqui a gente pode separar a parte que é água da parte que não é água, e com isso são gerados polígonos, né, que representam o corpo hídrico, e com esse polígono, com esse vetor, é possível gerar esse conjunto de pontos. Isso aqui representa a borda do reservatório. Isso é um conjunto de pontos que, para todos os efeitos, todos esses pontos possuem a mesma elevação, possuem a mesma cota. Então, isso aqui poderia ser considerado uma isolinha. Por essa figura, dá para entender como é que é feita a combinação, né? Então, aqui a gente tem perfil medido pelo satélite ICESat-2, é um satélite que utiliza um sensor a laser, que mede o nível do terreno. Uma vez que o nível do terreno está, né, disponível, e essa elevação está disponível, a gente pode fazer a intersecção das isolinhas que foram obtidas anteriormente com o nível dado pelo perfil do ICESat-2. Se a gente atribui a cota do terreno a essas isolinhas, a gente vai ter um conjunto de isolinhas que podem ser utilizadas para gerar um modelo digital de elevação, como esse que está mostrado aqui. Isso aqui já é o resultado do modelo digital de elevação, que no fim das contas é a própria batimetria. E com essa batimetria, a gente pode, por exemplo, construir uma curva cota área-volume, né, ou profundidade área-volume. E nessa figura são mostrados os resultados da área da superfície da água e do volume armazenado no reservatório, obtidos no trabalho, né, utilizando o sensoriamento remoto, e os valores obtidos com os dados oficial, né, com a batimetria oficial utilizada pelo órgão gestor. Essas curvas aqui são as áreas, né, aqui a gente tem a cota do nível da água, aqui a área, nesse sentido a área vai crescer, o verde é a área dada pela imagem, né, e pelo modelo digital de elevação. Houve uma tendência de superestimar o valor oficial, mas essa tendência ela foi reduzida quando a gente partiu para o cálculo do volume, né? Essas curvas aqui mostram o volume, nesse caso aqui está nesse eixo em milhões de metros cúbicos, o vermelho é o valor estimado a partir do MDE, do modelo digital de elevação, calculado com o satélite, o que mostra uma boa aproximação, né, no final, assim, de forma bastante ágil e de baixíssimo custo, foi possível reconstituir uma batimetria do lago, bem, comparado com o levantamento normal, o custo é infinitamente inferior. Bem, encerro por aqui, agradecendo mais uma vez a organização do evento pela oportunidade.
Obrigado, Alfredo, aí pela sua excelente apresentação e por trazer dados interessantes aí, contribuindo dessa forma aqui para o workshop. Nós temos duas perguntas aqui, uma delas é a da Marielle Gossetti, a doutora Marielle, ela quer saber what's a difference in skill between Sentinel-3, A and B?
Então, isso é uma discussão que tivemos, né, ao longo do trabalho. Houve uma tendência do Sentinel-3B ter melhor resultado, mas, ao mesmo tempo, é difícil dizer que o Sentinel-3B, de fato, é o que tem a melhor capacidade de representar o nível da água. Porque é relativamente simples de entender, se a gente considerar que a minha tela ainda está compartilhada.
Sim.
Tá, né? Então, como eu falei anteriormente, em 2012 iniciou um período de seca. O Sentinel-3A pegou praticamente todo o período de seca. E aí, esse período foi até 2016, 2017. Então, parte do período de seca o Sentinel-3A pegou. Então, isso pode ter influenciado os resultados do 3A. Enquanto que o Sentinel-3B entrou em operação após o término desse período de seca. Então, pode ser que os reservatórios que a gente utilizou, o Sentinel-3B, já tivesse uma condição melhor para a aplicação do satélite. Rigorosamente, no final, o Sentinel-3B deu resultados melhores, mas eu acho que não pode ser conclusivo, porque tem esses aspectos ambientais envolvidos também.
Ok, obrigado, Alfredo. Nós temos uma outra pergunta. O que falta, no seu entender, para poder usar a altimetria de maneira mais rotineira nos açudes e pequenos lagos do Nordeste?
Operacionalmente, eu tenho, não estou muito certo se isso pode ser utilizado operacionalmente Eu acredito muito que, voltando, né, àquela discussão a respeito de complementariedade entre as bases, né, in situ e satélite, serem utilizadas de forma complementar, nós temos um problema muito sério das séries, porque elas têm muitas falhas, né? Se vocês entrarem lá naquele sistema que eu mostrei da Ana, vai baixar os dados, ali está disponível tudo, mas pode haver situações em que realmente falta muito dado. Eu acredito que a altimetria para o satélite pode ser muito útil nessas situações de ajudar no preenchimento dessas falhas, né? Complementar a série de dados, tanto de nível como de volume. Mas aí, se a gente vai para aqueles reservatórios que realmente são muito pequenos, ou que estão fora do alcance da tecnologia no estágio atual, realmente acho que compromete bastante. A minha esperança, e acredito que seja a mesma dos colegas franceses, é de que o SWOT possa mudar esse cenário e permitir que a gente consiga enxergar aqueles reservatórios realmente de menor porte. Algo como 250 por 250 metros, isso dá em torno de 6 hectares. Então, se a gente pega um reservatório de 6, 10 hectares, é um reservatório realmente muito pequeno. Isso vai cobrir uma porcentagem muito grande daquele total de reservatórios que eu mostrei inicialmente e que existe no semiárido. Mas eu tenho esperança, sim. Eu também estou empolgado, né, com o SWOT.
Ok, obrigado aí pela resposta, doutor Alfredo. Tem mais uma pergunta, creio que você já respondeu, não passar aí, nessa pergunta anterior, mas o Rafael pergunta quais são as expectativas para monitoramento de reservatórios menores que 1 quilômetro?
Então, nessa linha mesmo. Eu acho que com a tecnologia que a gente tem atualmente, realmente é muito limitado nesse sentido. Mas eu acho que é um aprendizado também, né? Porque isso não quer dizer que não se deva investir nessas missões que estão em operação ainda. Eu acho que se deve investir no sentido de continuar a pesquisa, né? No sentido de continuar avaliando e testando essas missões que já estão operando, ou até mesmo as que já saíram de operação. Eu acho que isso tudo é um aprendizado e a gente vai entendendo melhor aquilo que serve, né, aquilo que funciona, aquilo que não funciona, que foi um pouco que eu mostrei já aqui no final sobre os impactos, né, das características do meio, né, das características ambientais. Talvez a gente fique muito com a cabeça no operacional, mas a parte científica também ela é importante. Então, mesmo que operacionalmente não seja promissor a utilização dessas missões, né, nos pequenos reservatórios, aqueles bem pequenos, muito pequenos, ainda assim, acredito que vale investir nisso e continuar esse estudo. Isso aqui que eu mostrei não é definitivo, muitas perguntas ainda estão em aberto.
Ok. Stefano, você gostaria de fazer um comentário também? Está liberado o microfone.
Stéphane, tu peux parler.
Stefano, can you talk now? Maybe Melissa can talk now.
Can you hear me?
Yes.
You hear me?
Yes, we can hear you.
Okay, so I just thank you for giving the word. I just wanted to add to your answer that after SWOT, Europe plan to that the following missions to the Sentinel-3, which are called Sentinel-3 New Generation, could be similar satellites as SWOT, which means also working in SWOT mode, interferometry, SAR interferometry, which means that if this is accepted, Sentinel-3, the successors of Sentinel-3A and Sentinel-3B will work in this mode, which means that we also will have full coverage, and in particular for these small objects, very small objects, we will have full coverage. So all the small objects will be monitored.
Good.
Hopefully.
Okay, thank you, Stefan. Melissa, nós temos mais alguns minutos. Se você quiser fazer a pergunta, sendo bem objetiva, o teu microfone está liberado. Melissa? Ok. Obrigado, doutor Alfredo. Obrigado a todos aí por nos acompanhar aqui nessa produtiva manhã. Tivemos palestras bastante interessantes. Aprendemos bastante aqui também sobre a nova missão SWOT. E, então, eu convido a todos, né, nós vamos encerrar, após a palavra da doutora Marielle, iremos encerrar a parte da manhã e esperamos vocês aqui a partir das 14 horas. Bom almoço a todos. Marielle, gostaria de fazer algum comentário?
Okay. My only comment will be thank you very much to everyone for those very interesting talks and also for the public to ask interesting questions. And we are looking forward to see you all at 2 o'clock.
Recording stopped.
We'll start talking another variable which is important for the hydrological cycle, and that is the precipitation. So see you all at 2 o'clock. Bon appétit in between.
Obrigado aos intérpretes por essa manhã e a gente retorna à tarde. Excelente.